Hi, my name is Matthew White and this is my engineering project proposal for CQUniversity Australia. The proposal is for a feasibility study for a 1 megawatt peak distributed solar array at the CQUniversity Rockhampton campus. I'm going to break this project down into its individual components. So firstly, the feasibility study on CQUniversity Rockhampton, it's actually going to be on the North Rockhampton campus. As you can see there's a lot of roof space available for us to plonk on some solar panels. What, though, does the 1 megawatt peak actually stand for? The peak watts is about the output power achieved by the solar installation under full solar radiation or perfect conditions. Deal, however, notes that the power returned by the panels in reality will actually vary with the weather and the sun conditions, and gives a range of around about 15 to 20% less than the megawatt peak value of what power will actually be getting returned in reality. So you can see over here that there's during the summer, the sun's actually angle of incidence is quite different to spring and autumn and winter, so there will be a lot of variation on those panels. Now, when we talk about distributed solar, we're referring to distributed generation, which means small power resources located close to the load points. So in this case, the load point would be the University North Rockhampton campus, and the power resource would be the solar panels plonked on the campus. So those solar panels would be transmitting power to the buildings around it rather than having to draw in power from the network outside of the university and pay the distributor for that power. The demand profile for the university is just here for 1 year, and we can see this is a time of day profile, so you can see that across the day there's generally a load of around about 800 kilowatts. And then across once we get to about 7 in the morning, the load goes up across the day and then it comes back down again. So if we were to get 800 kilowatts out of our solar panels all day, then we would just cut that whole chunk of the load off and we would only be buying this part here worth of energy from the distributor. Now, in reality, a lot of factors go into that, such as the temperature of the panels, the angle of the sun and the radiation that's coming down onto the panels and how much they're absorbing at any time of day. So what we can do with all that information, you can see there in these graphs that there's quite a lot of chaos in those figures. So we can push that all into a model and actually compare it against the load of the university and see what the solar panels will take away from that load and how it will affect the university's base load and the conditions there. So the benefits of this is that drawing in that weather data into a model gives us a more accurate forecast of what will happen, and we can then vary the amount of solar penetration that we have there and view what quantity of solar panels is actually the best. Is it really a megawatt that would do best for us, or should we perhaps install 800 kilowatts instead, or maybe go bigger, maybe 1.2 megawatts, because we have that 20% sort of drop on how much power the panels actually produce. This sort of thing enables the university to make better decisions when installing solar panels, and also it empowers the university to have an informed discussion with the distributor and actually to seek the greatest benefit for the university when in conversation with the distributor for a panel installation. Thank you very much for listening. Here's my reference list from this PowerPoint presentation. See you later.